Kalman filter in catastrophic filter divergence.
Thank you, and thanks for coming to my talk. So this was joint work with Andrew, who you all know, and Cody Law, who used to be at Warwick and is now at Caus. I also used to be at Warwick. I did my PhD and a postdoc there, but now I'm at... Oh, I need this microphone. But now I'm at North Carolina for a few months, and then I'm going to Quran for a few years. Anyway. So I'm going to talk about EnKF and what we can say about it, basically. So the structure of the talk will be first to introduce EnKF and maybe motivate it in some way, because a lot of you won't know what it is, I suppose. And then I'm going to talk about what we know about EnKF. And when I say know, I mean what we can prove. That section's quite short. It's about one slide. And then I want to convince you that maybe stochastic analysis might be a good tool to help us increase that section, so we can know a bit more about EnKF. So I'm going to set up a familiar framework. So suppose you have some deterministic model with a random initial condition. I don't think it really matters what type of initial condition you have, just suppose it's Gaussian. And I'm going to use the notation that the solution is the flow psi t of the initial condition. Not really important, I'll just refer to that again later. So you should think of this as being a very high dimensional and nonlinear problem. So the reason I say this is just because it makes lots of techniques useless. So just think that it's making lots of things useless, and so you've got to have new ideas to solve the problem. So we want to estimate the state at discrete points in time, separated by some observation, by some fixed time h. And we make observations at every time h. So you just think of an observation as some linear function of the truth perturbed by noise, and we're going to make the noise Gaussian. So here it's quite important that we make the noise Gaussian and independent at every point in time. We could probably work with other things, but that would make the talk quite different. So, of course, you can write down conditional density using Bayes' formula. But because it's high dimensional and nonlinear, this is completely horrible and useless. So it's unfeasible to do anything with the posterior directly. So we've got to come up with some techniques to try and use something about the posterior, or know something about the posterior, that doesn't involve using this as a function directly, using the density as a function directly. So what EnKF does, so EnKF is the ensemble Kalman filter, if you've never heard of it. So it kind of draws approximate samples from your posterior. And approximate samples is a non-rigorous statement. It sort of means that it comes from, one way of interpreting it is it comes from a real algorithm that in certain situations draws real samples from a posterior, and then we're applying that algorithm beyond the realm of which that is true, so it becomes an approximation. But I think it's a good way to think about it. So that real sampling procedure I'm talking about is called randomized maximum likelihood. So for linear models, you can really draw samples from the posterior in a successive way using randomized maximum likelihood. So I'll tell you what this is before I tell you what EnKF is, and the definition of EnKF is completely natural once you understand this, or once.
Can I ask a question?
Yeah.
Why do you call it randomized maximum likelihood and not randomized maximum a posterior?
I agree. I didn't name it that.
I know, but
yeah, it should be randomized.
And I think we shouldn't use the word anymore.
But I mean, people do that all the time. They call likelihood maximization actually posterior maximization.
Very confusing.
But, yeah. randomized maximum likelihood is really randomized maximum posterior. So this is just a very general problem that will illustrate what RML is. So suppose you have some unknown, and suppose it's distributed like a prior, like a Gaussian, and this is your sort of prior knowledge of it. Then you make an observation in the same way that we observe a state. So we kind of don't have any dynamics here. We're just assuming that there's some random variable and we have a prior on it. So we have one initial guess what it is, and then we observe it. And we want to know what the conditional distribution of this random variables is given the observation. So this is a nice simple case of an inverse problem. And so in the setting of filtering, this would really be the push forward of your previous guess. So the prior would be what you the forecast, what you expect given the dynamics. But here you don't really have to think like that. So what RML does is it takes a sample from the prior, so a set of independent random variables drawn from the prior, and turns them into a set of independent random variables drawn from the posterior. And they're conditionally independent given y. So, and this is exact. This is a real theorem in the case that I've set out here. If H is linear and everything's Gaussian, this is a real exact sampling procedure. So when I say a sample, I mean these are random variables distributed like this, and these are random variables distributed like this. So what do? You take your sample from the prior, and then we're going to create some artificial observations. So we take our real observation, and then we perturb it by noise, which is the same type of noise that was appearing in the observation. The same covariance and everything, but independent from the noise that appeared in the observation, because you don't know anything about that noise. And then you define an updated, so the UK, which is going to be our samples from the posterior, using a Bayes formula update. So this update works in the exact same way that you would update the mean in a usual Kalman filter or something like that. So you basically take this weight of your prior and the difference between your observation and sort of what you expect your observation to look like given the prior. And then you weight it with the Kalman gain. So it's not really the Kalman gain because we're in a sort of general inverse problem setting, but you know what I mean. And now this Kalman gain is computed using the exact covariance of the prior, so C hat. Okay? And so it's a theorem that these random variables are exactly distributed according to the posterior. It's a nice, easy thing to prove. Basically as hard as deriving the right things about the Kalman formula, about Kalman update. Okay, so that's RML. So ensemble Kalman filter uses the exact same idea, but with an approximation of the covariance in the Kalman gain. So things aren't linear anymore, so that means things aren't Gaussian anymore, but we're still going to do the same procedure and hope it works. So suppose you're given some ensemble at time j. For each ensemble member, we create an artificial observation, in the same way we did in RML. You take your real observation, you perturb it by noise, which is the same type of noise that appeared in the observation. And then you update each particle again using the Kalman update. So now you can see that the things that we U hats are now the forecasted, the flowed versions of our guess the time before, because that's what the prior is now the forecast of our previous guess. And now this is a Kalman gain, but it's computed not using the real covariance, because things aren't Gaussian anymore. The real covariance is kind of meaningless, but you use the covariance of the ensemble. So you're sort of thinking of this ensemble as a way of keeping track of what the distribution is, an empirical way of keeping track of what that distribution is. So in particular, you can use that ensemble to compute the covariance that you need to figure out the Kalman gain. So that's EnKF.
So in the linear case, everything is Gaussian, and so you're just about computing mean and covariance.
Yeah, but even in the linear case, this isn't the Kalman filter, because you.
Okay, so that's what I want to make sure I understand. In this case, don't you at the end simply assume that the push forward, which is no longer Gaussian, even though the initial condition were Gaussian and the noise is Gaussian, you just map it into a Gaussian again?
Well, not really, because you're using this empirical covariance, which isn't, even if they were Gaussians and you drew samples, the empirical covariance from those samples isn't going to be the real covariance.
So you're saying that even if the model dynamics is linear, and you start out with a Gaussian, then this is still an approximation because you don't use the true covariance but the sample covariance.
What if you had a lot of particles?
Yeah, it will converge.
It will converge to, so because you said something about the covariance being meaningless in this case, it would mean...
It's meaningless for fixed ensemble. I mean, it's not meaningless. It's
or if you increase the number of particles correctly, if you sample correctly...
So in a non-Gaussian case, the covariance isn't as meaningful as it is in a Gaussian case. That's what I meant.
Okay. You're projecting on a Gaussian asymptotically.
Sort of.
Do you have an intuition for why you have to add extra noise to the observation? I mean, I know that you have to do that to make it work. There was a paper 20 years ago.
So my intuition is because if you do it, it's a theorem.
It's true that if you do it, it's a theorem, but the observation already has noise.
So if you want something less mathsy, it's if you don't want to have to do a calculation to see it. It's because if you didn't do it, then your covariance in your analysis wouldn't take into account the covariance of the observational error.
I agree. I mean, from being one of the authors of that paper, you're referring to. It's very funny what you do, because in Bayes' theorem, we're trying to do a Bayes' theorem, of course. In Bayes' theorem, the observation is given. Everyone you have the state given this observation, and now we're generating a whole bunch of observations, which clearly there's something wrong in this interpretation, and I still haven't got my head around what actually goes on. It's clear that we are actually perturbing, at least in my view, perturbing h of x, so the observation of the model. That's what we are perturbing. And I think I'm almost there, but I still haven't got it.
If you figure it out,
how that works.
Yeah, I know you have to do that to prove the theorem, and your paper 20 years ago showed that.
No, but again, I mean, the interpretation, I think this interpretation is actually not correct. And the other one is correct, which you perturb h of x. Anyway.
Okay.
Is it important that the artificial noise has the same covariance structure as the real noise?
It wouldn't be. This wouldn't be a theorem if it was different.
There was no way to correct it.
I mean, it depends what you mean by important. If you want this theorem to be true, then it's important. If you want your algorithm to work, then maybe it's not important. I want that theorem to be true, so that's why I think it's important, but not everyone thinks that way.
You could you prove something else with different covariance?
There's samples from something besides the posterior.
Something from something from some other.
Of course you could.
And you could then gauge how off you are, right? What I'm saying, there could be another theorem.
Yeah, but why would you want to approximate something besides the posterior?
Maybe it's worth mentioning that there is a limit theorem of Leblanc, which proves there is a limit as n goes to infinity.
I was going to say that on the next slide.
Yeah.
So there aren't many theorems about EnKF.
Yeah.
But where there are theorems, they're about what happens when the number of ensemble members goes to infinity. So it's not surprising at all that if you took linear dynamics, as the number of particles went to infinity, you'd expect to recover the Kalman filter. Because your only approximation, if everything's linear, the only way you're approximating the Kalman filter is because you're using an empirical approximation of the covariance. And so if that covariance is approaching the right covariance, you'd expect that EnKF is approaching the Kalman filter. But theorems like that, the whole point of EnKF is that you want to use small ensembles, small relative to the number of dimensions. You don't want to use infinite ensembles. So you really want theorems about what happens when you have a fixed ensemble size. Maybe what happens in long time for filters of fixed ensemble size. So that's what I'm going to try and do. So this was the content of what do we know about EnKF. It's actually more than that, but I wanted to emphasize that not much is known about EnKF. So one thing that happens, one feature of the EnKF that's kind of nasty is filter divergence. Well, it's a feature of all filters. So ordinary filter divergence is when your filter trusts the forecast too much. It doesn't trust observations. You essentially get fixed on some trajectory that might have nothing to do with the real truth. So you sort of stay in a nice bounded region of the real solution because your trajectories are nice and bounded, but it has nothing to do with the real solution. So there's another type of filter divergence, which is much more exotic. So in certain situations, you can actually have that the ensemble blows up in finite time, even when your original dynamics were perfectly nice and bounded. So there's something, so this has been observed in some papers with John and Andy, Georg Gottwald, and sort of lots of combinations of those authors. So it's sort of a surprising thing that somehow the algorithm is injecting enough energy to blow up the procedure. And so this is known as catastrophic filter divergence. So what we'd like to investigate, well, we want to know what happens in the long time for ensemble Kalman filters.
Can you elaborate a little? Because this statement in some sense could be trivial. If I repeat drawing from a Gaussian, eventually, I mean, there will be a problem with machine precision because the tail extends all the way to infinity, so I can't represent it in the computer. But I suppose that this is not what is being said here.
I don't think it's the same procedure. I'm not sure. I think to get machine infinity from a Gaussian, you'd have to do
You need to wait.
a lot of draws, roughly
True, that's true. But if
square root of machine infinity or
if you are the
something.
one insisting on theorems that they hit infinity, and in that case, it will happen no matter what.
I can say I've drawn machine infinity from a Gaussian. I'm sure PDI has too.
Well, I don't know. Never noticed it.
Depends what your variance is, I guess. Anyway, so we wanted to prove some things about the long time behavior of ensemble Kalman filters. And this is a good place to start. Maybe can we at least understand if this is possible or if this is some kind of numerical artifact? If there's some real dynamical reason in the algorithm for this happening. And the framework that we developed kind of could be useful for saying stronger results, but at the moment, this is the only problem we're going to address. So now I'm going to make some assumptions on my dynamics. I think they're pretty much the same as what Daniel introduced yesterday. We have some kind of dissipative structure. So you have a linear plus bilinear form, and you have some linear, elliptic, and certain symmetries assumed on the bilinear operator, essentially to guarantee that certain energies are preserved and solutions always stay bounded. But this was the important point of catastrophic filter divergence, that you had bounded solutions for which the filter blew up. So now we have introduced a system where solutions are bounded, and in particular this includes 3D Navier-Stokes and the Lorentzes. So first I'll show you what we can do in discrete time. So think of h as being order 1. So that this was the observation frequency. So we're going to make a really big and restrictive assumption here, that we observe everything and the covariance of your noise is the identity, so in any dimension. Then you can find a constant that says your blow up is at most exponential in time. So these are our ensemble members, and we can say that the expectation squared of each ensemble member can be bounded by this term which grows exponentially in time. So you think that JH behaves like T, because that's how many steps you've taken times by the frequency of observations. And then this term is kind of all the bits that get added in by the noise. And these are still order 1, given that if h is order 1.
Can you say a bit why you require the covariance to be an identity? Could you just scale it out? Is it really a requirement? Just not diagonality, but the...
Yeah, I think probably the covariance, we could get away with one of them not being the
The
identity.
important thing is that it's just diagonal rather than
Oh, yeah.
identity.
Yeah,
Right?
yeah. But there's lots of ways that you could make it a bit more general.
Yeah, I was just wondering if it's important that it's...
No.
It is important that we observe everything.
Yeah,
That is
but
important, yeah.
That I was wondering if it can be another number along the time.
So essentially the way the proof works is you just figure out all the worst things that could happen at each step of the procedure. It turns out that they add up to something that's not too bad. It's only growing exponentially in time. In particular, it doesn't look like you could have finite time blow up from one of these procedures. So this suggests, at least in discrete time, the blow up is a kind of numerical phenomenon. When did I start?
The hour.
Okay. So, unfortunately, this doesn't work so well when h goes to 0. So we always expect this to be of order t, like exponential of t, no matter what h is, because jh should behave like t. So that term's fine. The numerator there is fine, but the denominator isn't fine. That's going to blow up.
Can I ask a question?
Yeah.
So the catastrophic divergence that people have talked about, was that discrete or continuous?
Discrete.
I thought it was discrete.
Yes.
And you're proving here that they had a numerical problem.
But that's if you're observing everything.
Yeah.
Okay, yeah.
If you're observing everything,
Okay.
then they had a numerical problem.
Yeah, okay.
But they have fairly sparse observations.
Yeah.
I think they had like a 6-dimensional.
If you don't observe everything, then it might be...
Yeah, exactly.
I don't know.
Yeah.
I don't know. But
No, I understand. Okay, yeah. Thank you.
So in the continuous time case, I'm going to illustrate what things look like when h is not the identity. I could also do that here, but it's more interesting in the continuous time case. So if observations are really small, you probably need another approach because those estimates don't look too good anymore. And definitely if you wanted to do continuous time, it's not going to work by just taking a limit of that argument. But actually there's other things that come in when you do continuous time. You often scale your noise differently depending on how frequently you observe. So you might have to blow up your noise a bit. Okay, so this is the only calculation in the talk, and it's going to be about how to derive a continuous time limit of the ensemble Kalman filter. So really I'm going to take our update equations and rewrite them until they look like a numerical scheme for an SDE or an SPD. It's very formal, but you can sort of see that this is the only limit you could possibly expect. So you start with the update equations that I already introduced. Now we expand the Kalman gain. So this is the formula for the Kalman gain. And now we're using this empirical covariance that was the covariance of your whole ensemble. And haven't done anything else there. So then we subtract uj from both sides and divide by h. So this is starting to look like the discretization of an ODE or a PDE or something. So here this looks like discretization of the time derivative. This looks like discretization of your vector field because it's the derivative of the flow. This kind of just looks like noise. It probably isn't scaled in the right way because you end up having something that's order 1 over h, and these are probably going to behave like Gaussians, and they won't really show up if you do that, or they'll be too strong if you do that. So you have to scale something. So we rescale the covariance so that the noise actually shows up in the limit. So you either get sensible answers instead of either trivial answers or infinite answers. So we pick the scaling so we replace the covariance with a blown up version of the covariance. It turns out this is the only choice you can do that makes sense in a limit, or doesn't give you something trivial.
But that's a little strange, isn't it? If you look at the textbook derivations of the Zakai equation, they usually assume that the noise is an Ito, that the observation is an Ito process, which would mean that if you discretize that the noise term goes like root.
But this is behaving like white noise, not like a Brownian motion. Whereas if you think about the Ito process, that's the integral of white noise. So we're kind of replacing things at the level of the white noise. Okay, so what have I done here? I've made this substitution, and I've also put in our expression for yj plus 1k. So that's all this garbage here. So we had our truth plus the noise from the original observation plus these sort of fake additional noise we put in there. So now we can approximate a lot of terms here. So for instance, you know that if you take the flow of something, it's equal to something plus something equal to h. Okay? So everywhere we see, well, except here, wherever we see in here a psi of h, we can basically replace it with a uj, with the initial condition of the psi. And then this nasty empirical covariance simplifies a lot as well, because we can use this trick within the covariance. And you see that the covariance of the forecast looks approximately like the covariance at time j of the ensemble plus an error of order h. So everywhere you see this c hat j plus 1, you can replace it with what I call c of uj, which is the empirical covariance of uj, so of the forecast at time j. Or it's really time jh, if you like. So what do we end up with? We end up with something that looks a fair bit like the discretization of an equation. So time derivative, vector field, you've got some sort of dissipative thing here, and then you've got a bunch of noise here. So it's easy to see that the only possible thing this could converge to, if it will converge at all, is an Ito S stochastic, maybe P dE, depending on if you're finite or infinite dimensional.
That thing that you said is dissipative, is it obvious that it's always dissipative, the second term?
No.
Ah, okay.
This is the key point, the
this
key problem of the paper, actually. Good eye, very good eye. So it might be dissipative or it might be the opposite. So anyway, we've got a fairly nice looking equation for the sort of limit of the ensemble. So it's a system, a coupled system of stochastic equations, and each point in that system represents one ensemble member, and they're only coupled through the covariance and the observation, I suppose. So, and you notice that this derivation was for any h and any gamma. So when I made those assumptions on the observation and the covariance, that was just to prove that thing in discrete time. But if I want to derive the continuous time limit, it doesn't work for anything.
W is a Wiener process, right? What's B?
Another Wiener process. So here we had two separate
So
noise increments, and they were independent.
Symbols for the same type of stochastic process.
Yeah, but they're independent.
Right. Yeah.
So this one, this Brownian, so this Wiener process comes from these artificial pieces of noise. So I've cleverly swapped the order of them around. And the B comes from the noise in the initial observation. So they're really independent of each other. So just having this equation is kind of nice, because you can understand, for the dynamics of this equation, you can understand a lot of things that people intuitively know about the ensemble Kalman filter. So for instance, if this is dissipation, which it might not be, but let's just assume it is, you only see differences. So it wants, if it is dissipation, it wants to bring you closer to the truth. It wants to make your particles look more like the real signal. But it only sees differences in the observed space, which is natural. You only correct things that you can see. You're not going to make corrections to things you can't see. Moreover, it only makes corrections. So the range of this dissipation term is the space spanned by the ensemble. So So the range of the covariance will be the space spanned by the ensemble. So you're not going to be able to help yourself in directions that aren't spanned by the ensemble. That's why it's important to keep some kind of spread in the ensemble. So just being able to write this equation down tells you nice intuitive things about the EnKF. You look like you're frantically writing the equation down. Should I wait a bit? No. So the second observation you can make, so suppose that your dynamics were linear for a second, then what happens? So if your dynamics were linear, and then we write the mean of the ensemble, then you can write an equation for the mean. So because you're assuming f is linear, it just comes inside. Everything comes inside the covariance, and you get a sort of nice expression for the mean of the filter in the linear case. And so this is exactly the expression for the Kalman-Bucy filter plus a sampling error. Okay? Which is, of course, what you'd expect, because EnKF, like we'll go on prove, is a Kalman filter plus sampling error. And so you can do the same thing for the equation for the covariance as well. So when we make this, for this equation, this stochastic PDE or SDE, so suppose that this system UK satisfies that equation, which I labeled by a green dot. And again, suppose that H and gamma are the identity. And then let E be the error between that ensemble and the real truth. So it's just more convenient to deal with the error rather than the ensemble itself. Then we can prove a similar type of estimate to what we had before. So the ensemble blows up no faster than exponential. So the estimate looks a bit more complicated because we're not just looking at the L2 norm anymore. We're looking at the L2 norm and then averaging it over all the ensemble members. Of course, that's kind of stronger because you could bound every term in there by the sum. Well, with some factor of k there. So it's just as good as the previous estimate, or better actually. But it has this extra averaging in there. And this averaging is really important. The theorem wouldn't work without you putting that averaging in there. So you can think that you're taking an average not only over the randomness that comes through observations and all the perturbations you put in there and the initial conditions. There's also the randomness that comes from thinking of your ensemble as an empirical approximation of a distribution.
So beta depends on capital K.
I don't think so.
No?
No. And it's really, so this idea that you need to average over the ensemble members is really important. The proof wouldn't work at all without that. There's a magical cancellation that occurs when you sum them up that doesn't otherwise. So it suggests, again, that in this simple case, catastrophic filter divergence is some kind of numerical phenomenon because you're only blowing up at most exponentially. So you're not going to blow up in finite time. So I just want to explain very briefly why we need this really restrictive assumption on the observation operator. If you look at this equation, imagine how you're going to prove something about this. So intuitively you think you're pumping lots of noise in there, so if you're going to get blow up, it's probably because you're pumping too much noise in somehow. And if you want to control that blow up, you'd have to control it with this thing that looks like it should be dissipation. So in some sense, the energy pumped in has to be cancelled out, or has to be balanced by the contraction. So if you want this to really be dissipation, then you want this operator to actually be positive definite. But there's no reason for that to be positive definite. So it's a product of two matrices. Both of those matrices are positive definite. The product of two positive definite matrices isn't necessarily positive definite. So you don't know that this product is positive definite. And so there's no telling if this is actually giving you the right sort of dissipation that you need. And the only reason, the reason that we can prove our theorem is that in the nice case where you choose this, you sort of get a lot of cancellations that occur here. So you don't even care if this thing's positive definite because it disappears in the limit. Actually, no, at some point you might care that it's positive definite.
But if I
This is what
sorry, but if I make H the identity matrix here, oh, of course, no,
It's
I
still-
see. Gamma is the identity matrix.
Okay, so as a young speaker, I've fulfilled my duty to finish on time. So writing down.
Take this personally.
So writing down an SD or SPD, it allows you to see the important quantities in the algorithm. So at least for someone like me, someone like a mathematician who understands stochastic equations much better than they do algorithms, this is a good way to represent the EnKF. And it might be an essential way to represent it in continuous time. And so we can't prove that catastrophic filter divergence is a numerical phenomenon, but it's a decent starting point. Or it might give you another place to investigate what could be going wrong, what could possibly be going wrong. So you'd know that if you want blow up, maybe that operator would have to not be positive definite. So you could do some kinds of checks. So there's obvious directions for improving this. Can we improve the condition on H? It's not clear to me how you do that right now, but it would be something to do with identifying when this is positive definite. It seems like quite a difficult problem because this is really moving around all over the place. It depends on your ensemble. But another thing it points out is that if you can actually measure these important quantities during the algorithm, maybe you can test live how well your algorithm is doing. So you actually have access to all the things that appear here. You know what that is during the algorithm. So you could check, is it positive definite? Or even, is it bounded, does it have a lower bound? Do you know how good it's doing? So you can have a theorem that says, if there's something you can check during the algorithm is true, we know the algorithm is doing this well. So that's something else I'd like to work on. Okay, thank you.
Excellent timing. Do you have time for questions?
That was great. I really liked that a lot. All really good talks, brings up lots and lots of questions. The first one is, you made a lot of assumptions to get there. Or of course, you had to in order to get. And one of the assumptions you made was that the dynamics were linear in order to get your final.
No.
No, I thought you had an M in there. I did go by them.
So there's two observations. There's some remarks I made. One of the remarks I assumed was linear, and I said then you get common juicy.
Okay, fine. That I guess my question is, can you kind of square the circle for me? And is there, in the cases that have been demonstrated in the papers that you cited of catastrophic blowup, is there some particular setup that provokes it? Can you say anything about when this occurs?
They all fit into this framework. This one. So I think in the paper they mentioned that you need to have some kind of like a slow manifold, some kind of set that you get strongly contracted to.
Mm-hmm. So, but say in Lorentz 63, so they have an example in Lorentz.
There's definitely in Gottwald, Maida, they do Lorentz 96.
And they actually made it explode with frequent observations of the whole state vector?
No. With partial observations. It's something like 6-dimensional, and then they observe 1 point.
But frequent observations.
Yeah, frequent observations.
And it explodes.
Yeah.
That's bizarre.
And I think Dennis McLaughlin has an example of Lorentz 63, which is very much the same. same spirit as the
Never saw anything like that.
You think?
So I'm kind of asking about this positive definiteness. So is it, I mean, it's a bit kind of just a while. Is it possible to symmetrize and to modify the scheme so that we get a symmetrized version of
Yeah.
MSH?
Yeah, I mean, there's lots of, mathematicians can come up with different schemes that could make this work, I think. So we were speaking about doing that at one point,
Yeah.
and then I left the country.
There is something called email. Maybe also it's worth mentioning that there's this thing called variance inflation, which would correspond to, say, adding a multiple of the identity to C. And if you do that, you can prove stronger results.
Yeah.
You can prove contraction to the truth rather than just boundedness.
So there might be in principle two mechanisms, at least in the continuous time, for the blowout. Like
Yeah,
one,
so-
that the product is not positive definite, and the other one could be if H was rank deficient, right? Meaning, I mean, if you
That would make it not positive definite, wouldn't it?
But
That would be a subset of the first
yeah,
problem.
okay, it will be the same, yeah, it will be the same. Yeah, you're right. Yeah.
Doesn't that already prove your answer? If you measure the whole equation, don't you
Measure, you mean? Like,
put the H operator on top of the whole equation?
Oh, yeah. So you mean try and prove things in a space such that the thing that appears here is definitely positive definite? Is positive definite?
Yeah.
Yeah, we tried that, and the cancellations that you need, the subtle cancellations, don't work anymore if you do that. So, yeah, it seems difficult.
You take a different combination then of the matrices.
Yeah,
So you take
there might be
P and
there might be some weird space. Yeah, you might be able to pick some strange space.
weird.
Well, I mean, I didn't mean weird like physically weird. I meant weird just you define it in a weird way.
Yeah.
So here you're assuming that you're taking observations, and even though you're taking them more and more often, they remain completely independent. Isn't an interesting generalization to try to see if you model them as themselves as a process?
But yeah,
A
so
process in time where you would have some correlation in time, which means that they actually
Yeah.
decay.
So if you go back to this scheme, so if this was a sequence, like if you think these are increments of a random walk, then you expect to have some kind of SDE in the limit. If that was a correlated sequence, you don't necessarily get Ito SDEs. You might get some
You
weird
might
correction. or
get, you know,
something.
you might get their process and then something else that is coupled too, which would be
Yeah.
whatever equation is actually telling you all the observation are
Yeah.
evolving.
Yeah, that could be interesting.
Would this help, or do you think they would be?
I mean, it would relax your assumptions.
Is it the divergence related to the fact that you're taking more? I mean, you're putting more and more noise in this thing because you're always assuming that your observations are independent, or no?
But perturbing by white noise, that's what you usually do when you do filtering in continuous time. So if you, like stochastic filtering, the observation is an SDE, and it's said like, you know, dy. Sure. So the observation looks like H of C plus CW.
Mm-hmm.
So this would be the integral of our y.
Right, so don't you want H of V dt?
Yeah.
Yeah, that's what I was asking.
But if you wanted a process that's smoother than that, then you wouldn't end up with an SDE. You'd get some kind of random mode. Like if you weren't perturbing by white noise, if you're perturbing by something like Brownian motion.
No questions? Okay, well, saying it again.